Earth holds secrets, not in hidden chambers, but in its very fabric, in the silent architecture of stone and sediment. Yet this architecture is less a careful library and more a voracious furnace, constantly consuming its own history. We stand on a planet that forgets, that actively erases its past with a relentless, indifferent hand. This process of forgetting is not rapid. It is a slow, grinding mechanism of deep time, leaving only fragmented whispers for us to decipher, clues that are more often absences than presences. Consider the Grand Unconformity, a phenomenon etched into the very bedrock of our world. These are not merely gaps in a sequence of rocks. They are chasms of lost time. Imagine layers of rock laid down over millions of years, then tilted, uplifted, eroded away completely, and finally submerged again to receive new layers on top of the ancient, now exposed. Stumps, millions, even billions of years can simply vanish, taking entire histories with them. What forms of life flourished during those vanished eons? What complex ecosystems rose and fell? The rock record offers no answers, only a stark, smooth line where entire chapters of planetary evolution were simply torn out. This geological amnesia is a fundamental truth of our existence, a constant reminder of how little we truly know, what secrets might be buried, or rather unburied, and then reburied in these vast, silent intervals. And real quick, make sure to subscribe and hit the notification bell for more videos. Now let's keep going. Beneath the restless oceans, an even more profound erasure takes place. The oceanic crust, the vast floor of our planet's watery expanse, is locked in a perpetual cycle of creation and consumption. At mid-ocean ridges, new crust is born, swelling from the mantle's depths. But this expansion is balanced by an insatiable maw. Subduction zones. Here, ancient oceanic plates dive back into the fiery interior of the Earth. Imagine the scale of this process. Entire sea floors, stretching for thousands of kilometers, are inexorably dragged down, melted, and recycled. Any seafloor-dwelling civilizations, any complex ecosystems that might have thrived on these ancient plates, are consumed without a trace. Their existence is ephemeral, their eventual fate sealed from the moment their crust was forged. There is no fossil record of these imagined deep-sea empires, no sedimentary layers to tell their tale. The ocean's depths are a conveyor belt to oblivion for all but the most fleeting impressions. Our very atmosphere also plays a role in this grand forgetting. The delicate balance of atmospheric chemistry and climate cycles dictates not only the conditions for life, but also the potential for its preservation. Imagine periods when atmospheric oxygen levels were drastically different, or when global climates were extreme. Such conditions can prevent the formation of organic material or hasten its decay, making fossilization an impossibility. The air we breathe, the winds that sculpt the land, the rains that etch the mountains, these are not merely passive elements. They are active agents in obscuring the past, preventing the very marks of life, or indeed the markers of any forgotten events, from ever reaching us. An entire epoch of biological or even geological transformation might leave no more than a faint chemical signature, a ghostly whisper in ancient ice cores, rather than a clear narrative in stone. The landscape itself conspires in this silent erasure through geomorphic smoothing, erosion, sedimentation, and tectonic uplift work in concert over immense timescales to flatten uneven terrain, burying or obliterating surface structures. Consider mountains, sculpted and worn down by wind and water, their material carried downstream to fill ancient basins, creating vast, featureless plains. Any structures built on these mountains, any signs of complex activity, would be ground into dust, diffused into the sediment, becoming indistinguishable from the natural world. The Earth's surface is constantly being resurfaced, like a canvas perpetually repainted, wiping away previous strokes with each new layer of dust and stone. Even the fossil record, our most cherished window into deep time, is fraught with profound gaps. Fossilization is an exceptionally rare event. The vast majority of life, from microscopic organisms to mighty beasts, decomposes without leaving any lasting impression. Specific conditions are required: rapid burial, low oxygen environments, the presence of minerals for even a fleeting outline to be preserved. For complex societies, the chances are astronomically smaller. Buildings crumble, tools corrode, and organic remnants decay. The silent earth holds countless tales that will never be told, not because they are hidden, but because they simply ceased to exist, leaving no trace. This extreme rarity means that what we see as a history of life is less a complete tapestry and more a few scattered threads, glimpses into isolated moments. How then do we begin to reconstruct the truly ancient past? A past where even the most basic evidence is systematically removed. We must look for the most subtle and unusual patterns, the echoes of forces that transcend even the planet's vast propensity for forgetting, patterns that might hint at a deeper, more profound rhythm to existence itself, leading us to consider the cosmic breath of our solar system. Our journey traces backwards, beyond the familiar fossils and geological layers, into a realm so profoundly alien it scarcely resembles the world we inhabit. We are venturing into the Pre-Cambrian, a vast stretch of time encompassing nearly 90% of Earth's entire history, where the very fabric of our planet was forged and reshaped. Here, life itself was a desperate whisper against a backdrop of cosmic violence and chemical extremity. The earliest chapter of this deep past is etched in the Hadean Inferno. Imagine a newly formed Earth, not as a blue marble, as a swirling crucible of molten rock. The surface was a continuous panorama of erupting volcanoes, painting the sky with ash and superheated steam. There were no stable oceans, no solid ground to speak of, only a restless, glowing surface, constantly pummeled by remnants of the solar system's formation. Asteroids and comets, a cosmic artillery bombardment, cratered the developing crust, each impact releasing unimaginable energy, vaporizing nascent oceans as fast as they could condense. This was a planetary hellscape, a testament to raw, untamed forces, a world where the very concept of life seemed an impossible dream. Yet within this chaos, the elemental ingredients for life were being stirred, waiting for a moment of quietude, a subtle shift in the cosmic breath as the bombardment eventually lessened and the planet began its interminable cooling. The Archean Aeon emerged, the constant downpour of impacting bodies gave way to torrents of rain, gradually filling the deepest basins. These were the Archean oceans of iron, vast liquid expanses, unlike anything we see today. They were not blue, but likely a murky green or rust red, saturated with dissolved iron leached from the cooling crust. The atmosphere above these primordial seas was thick with methane, ammonia, and carbon dioxide, a toxic cocktail by modern standards, blocking out most sunlight and creating a perpetual twilight. Yet, in these inhospitable waters, a miracle began to unfold. Simple, single-celled organisms, the first bacteria, arose. They were anaerobic, thriving in the absence of oxygen, feeding on chemical energy, developing the slow, deliberate processes that would eventually reshape the entire planet. But this nascent life carried within it the seeds of a profound, destructive transformation, one that would lead to a planetary cataclysm. This transformation was the Great Oxygenation Events Cataclysm. For over 1 billion years, these early, humble life forms, particularly cyanobacteria, slowly began to photosynthesize, using sunlight to convert carbon dioxide and water into energy, releasing oxygen as a waste product. This oxygen, initially absorbed by the vast quantities of dissolved iron in the oceans, began to accumulate. The rusty bands found in ancient rock formations are a stark testament to this process, as iron precipitated out of the water. But eventually, the oceans could hold no more. Free oxygen began to fill the atmosphere, a poison to the anaerobic life that had dominated the planet for so long. This was the first, and perhaps most significant, mass extinction event, not caused by an asteroid or volcanic eruption, but by life itself. The world was utterly remade, setting the stage for more complex forms, though the transition was anything but smooth. In the wake of this planetary upheaval, as oxygen continued to accumulate and the Earth stabilized, came the Ediacaran enigmas. This period, preceding the Cambrian explosion, reveals a world populated by strange, soft-bodied creatures, unlike anything alive today. They were flat, quilted, and often sessile, lacking mouths, digestive tracts, or even obvious organs. Disc-shaped forms, frond-like organisms, and segmented mats clung to the seafloor, quietly absorbing nutrients from the water. They represent a distinct, almost experimental phase in the evolution of multicellular life, a tree of life that branched off and then, for reasons still debated, vanished. The fossil record of these peculiar beings is scarce, their soft forms rarely preserved, adding to their mystery. Their disappearance marks another profound shift, posing questions about the forces that drive extinction on a global scale. This vanishing era leaves us wondering about the next great chapter, which would unlock the potential for truly complex life, a story of an explosion of forms, the Cambrian, and the strange forces that triggered it. The geological record, until this point, has whispered of microbial mats and enigmatic soft-bodied forms. Then, with a sudden, astonishing flourish, the whispers become a roar. We enter the Cambrian, an epoch that saw life on Earth undergo its most spectacular transformation, a biological Big Bang that fundamentally reshaped the planet's tapestry. Almost all animal phyla known today, the fundamental blueprints for body plans, materialized within a geologically brief span of only 20 to 25 million years. This was not a gradual unfolding, but an abrupt, almost bewildering emergence of radically new forms. Before this period, the fossil record showed little hint of the intricate, complex organisms that suddenly dominated the seas. Hard shells, articulated limbs, compound eyes, and specialized organs appear as if from nowhere, painting the ancient oceans with an unimaginable palette of life. The diversity isn't just in species count, but in the sheer architectural innovation. It's a profound shift, a sudden blossoming that still challenges our understanding of evolutionary mechanisms. Beneath this explosion of forms lies a deeper, more fundamental change, the emergence of regulatory genes. Specifically, the story of Hox's genes offers a profound insight into this biological revolution. These master control genes dictate the body plan of an organism, determining where limbs grow, where segments form, and how organs differentiate. A small change in a Hox gene can lead to a dramatic reordering of an entire body structure. It was as if evolution suddenly gained access to a sophisticated genetic toolkit, allowing for a rapid experimentation with countless variations on a theme. The proliferation of these genetic switches allowed for the swift generation of novel body plans, setting the stage for future evolutionary trajectories, a blueprint for all that would follow. This sudden burst of complexity did not occur in a vacuum. It ignited an evolutionary arms race with the appearance of actively moving, predaceous animals, new pressures emerged. Creatures developed hard external skeletons, not just for support, but for defense against newly evolved hunters. Spines, armor plates, and burrowing behaviors became vital for survival. In turn, predators evolved sharper claws, more acute senses, and more cunning hunting strategies. This dynamic feedback loop, where every innovation by prey drove a counter-innovation by predator, and vice versa, accelerated the pace of diversification. Each new adaptation created a fresh challenge, pushing life towards ever greater complexity and specialization. The oceans became a crucible of evolutionary innovation, a theater of survival where the stakes were constantly rising. But what triggered this cascade? The stage for this grand drama may have been set by monumental shifts in the Earth's environment. For millions of years prior, oxygen levels in the atmosphere and oceans were relatively low. The Great Oxygenation Event had occurred much earlier, but the full oxygenation of deep ocean waters was a slow, uneven process. As oxygen levels finally climbed to crucial thresholds, it powered more energetic metabolisms, allowing for larger, more active bodies, perhaps a critical global warming phase, or a series of glacial melt events drastically altered ocean chemistry, releasing vast stores of nutrients and creating fertile grounds for biological innovation. These environmental triggers, combined with the genetic potential unlocked by Hawk's genes and the escalating arms race, converged to create a unique moment in Earth's history. But to fully grasp the significance of these changes, we must look beyond the immediate explosion of life to the very foundation of the Earth itself. For the tectonic forces at play would shape every subsequent chapter. Beneath the swirling oceans and shifting atmospheres, the planet's very crust was undergoing transformations of immense scale. The story of Gondwana begins not with a sudden birth, but with a patient, relentless process of deep time. Ancient cratons, fragments of forgotten continents, drifted across primeval seas, drawn together by the Earth's internal furnace. It was a slow collision, a tectonic ballet, unfolding over hundreds of millions of years, as landmass after landmass sutured itself to its neighbors. The result was a titan, a supercontinent so immense it dominated the southern hemisphere for an epoch, its ghostly presence still echoing in the bedrock beneath our feet. This assembly of the southern giant was not a gentle joining. It involved colossal mountain building events, scraping and folding the crust, leaving scars that trace its ancient boundaries. The very architecture of the earth was being rewritten, forming a foundation that would dictate the flow of oceans and the path of evolution for countless ages. Within this colossal landmass, life found its footing in diverse and often extreme environments. Gondwana developed vast interior deserts, sun-baked and barren, where winds scoured the ancient rocks. These heartlands were unforgiving, yet they played a role in shaping atmospheric circulation and rainfall patterns across the globe, but along its extensive coastlines, where the supercontinent met the ancient oceans, vibrant ecosystems thrived. Lush forests, primitive plants, and early animal forms adapted to these margins, where life found sustenance and shelter. The interplay between the parched interior and the nourishing coasts painted a picture of stark contrasts, influencing how species spread and diversified across the landmass. This geographical duality created unique evolutionary pressures, seeding biological innovation that would later fan out across the planet. For a period, Gondwana became the stage for one of Earth's most profound climatic events, a gripping Permian ice age. Immense glaciers, kilometers thick, spread across vast swathes of the supercontinent, particularly over what would become Antarctica, Australia, India, and parts of Africa and South America. These great sheets of ice-carved valleys deposited massive erratics and left indelible marks on the geological record, evidence of a time when much of the southern world was locked in a frozen embrace. The sheer scale of this glaciation cooled the entire planet, altering sea levels and ocean currents, and setting the stage for significant shifts in life forms adapted to these colder conditions. The geological signature of this deep freeze is still visible today, a silent testimony to the planet's ability to swing between extremes. But no landmass, however vast, is eternal. Gondwana's reign was destined to end with an equally monumental process, rifting and drifting apart, driven by the ceaseless convection currents within the Earth's mantle. Cracks began to appear, slowly at first, then widening into vast new oceans. This inexorable breakup saw the supercontinent tear itself into the familiar continents we recognize today. Africa separated, then South America, followed by the Indian subcontinent, Australia, and Antarctica. Each fragment embarked on its own long, solitary journey, drifting across the global ocean. This fragmentation not only reshaped the Earth's surface, but profoundly altered oceanic circulation, creating new currents that redistributed heat and nutrients, and influencing global climate patterns for millions of years to come. The long isolation of Gondwana and its later dramatic fragmentation left an unmistakable biological footprint. As the pieces drifted apart, populations became geographically separated, evolving in isolation for millions of years. This process led to an extraordinary degree of biological endemism, where unique species developed on each of the newly formed continents, found nowhere else on Earth. The marsupials of Australia, the unique flora of South Africa, the ancient lineages found in South America. These are all living legacies of Gondwana's long history. Even today, the genetic echoes of this supercontinent can be traced in the distribution of plants and animals, a testament to to the profound influence of tectonic forces on the tree of life. This intricate link between land and life prompts us to consider the next great puzzle: the planet's deep atmosphere and the violent events that reshaped its very composition. There are moments in the Earth's long calendar when the very breath of life seems to falter, when the intricate tapestry woven over eons unravels with terrifying speed. None were more profound, more utterly devastating than the event known as the Great Dying. This was not merely a thinning of the ranks, but a wholesale erasure, a cosmic reset button pressed by forces almost incomprehensible in their scale. We speak of numbers that defy easy comprehension. Over 90% of all marine species simply ceased to exist. Their fossilized remains vanish from the rock record, leaving silent gaps where bustling ecosystems once thrived. On land, the devastation was only slightly less complete, with 70% of terrestrial vertebrate families disappearing forever. Imagine a world where entire branches of the evolutionary tree are pruned away, leaving behind only scattered, tentative shoots. The sheer breadth of this obliteration suggests a cause equally vast, a planetary wound that left no corner untouched. What force could unleash such a widespread, indiscriminate purge? The deeper we look into the planet's scarred memory, the more unsettling the answers become. The prime suspect, a dark heart beating in the Siberian wilderness, offers a chilling explanation. Known as the Siberian Traps, this was not a single volcano, but a massive flood basalt event, a colossal outpouring of lava that covered an area the size of Western Europe. For 1 million years, fissures in the Earth's crust bled molten rock, relentlessly pumping greenhouse gases into the atmosphere: carbon dioxide, methane, sulfur dioxide. These ancient exhalations began to choke the planet. The sheer volume of these eruptive events is almost beyond imagination, pushing the Earth's climate system to a breaking point. It was a slow-motion catastrophe, an inferno not of fire, but of invisible gases, silently altering the very fabric of the air we breathe. As these gases accumulated, a runaway global warming event took hold. The oceans, once vibrant with life, began to warm, their waters less able to hold dissolved oxygen. This led to a suffocating phenomenon called ocean anoxia. Imagine vast stretches of the seafloor becoming silent, lifeless plains, their depths devoid of the oxygen needed to sustain complex organisms. The expansion of these dead zones climbed ever higher in the water column, squeezing marine life into ever-shrinking refugia, until even those pockets could not sustain the sheer biomass they once held. It was a silent, creeping death, layer by layer, as the oceans slowly turned toxic, with hydrogen sulfide from anaerobic bacteria thriving in the oxygen-depleted waters. On land, the situation was equally grim. The colossal volcanic eruptions didn't just release greenhouse gases, they also spewed vast quantities of sulfur dioxide into the atmosphere. This reacted with water vapor to create sulfuric acid, raining down indiscriminately. Acid rain on an unimaginable scale withered forests, poisoned soils, and stripped nutrients from ecosystems. The skies themselves turned toxic, filled with sulfurous compounds that further blocked sunlight, creating cycles of warming followed by brief, jarring periods of volcanic winter. It was a planet transformed, a landscape of acid-scarred rock and dying vegetation, with the air itself a weapon. Life caught between the fire above and the poisoned waters below faced an existential threat unlike any before or since. The aftermath of the Permian extinction was a testament to both the fragility and the enduring spirit of life. The planet was utterly remade, scoured clean of its previous inhabitants. Recovery was not swift. It took millions of years for ecosystems to even begin to resemble their former complexity. New species arose from the ashes, diversifying into the ecological niches left vacant. But the scar on the Earth's history remained, a stark reminder of how quickly paradise can be lost. It demonstrated that life, though tenacious, is utterly dependent on the delicate balance of planetary systems. This profound lesson about planetary vulnerability leads us directly to another dramatic shift. The very air that fueled this catastrophe, and how it came to be in the first place. During the Great Oxygenation Event, the shadow of the Permian extinction receded slowly, unveiling a world primed for new architects of life. From the crucible of that global catastrophe emerged creatures that would define an epoch, not just by their presence, but by their sheer scale and unprecedented longevity. This was the Mesozoic era, a span of time where life itself seemed to exhale and expand into forms, both magnificent and terrifying. In the Triassic period, the first whispers of these giants began. Small, agile, and often bipedal, the earliest dinosaurs were not yet the colossal beasts we imagine. They were survivors, adapted to a newly harsh and often dry landscape. Their unique hip structures, allowing for an upright stance, gave them an edge over the sprawling reptiles that still dominated. This biomechanical innovation meant greater efficiency in movement, a crucial advantage in foraging and escaping predators. The supercontinent Pangaea still held sway, ensuring a relatively uniform global climate, though with stark seasonal variations. This early adaptability, a silent testament to evolutionary pressures, set the stage for a dramatic rise. But their path to dominance was not immediate. It was a slow, deliberate ascent that unfolded over millions of years, as if the Earth itself was preparing for its next grand statement. As the Earth spun into the Jurassic, the world transformed. Pangaea began its slow, deliberate fracture, allowing for greater moisture penetrate the continental interiors. This shift nurtured vast, lush forests, a verdant canvas upon which giants would roam. Here, the sauropods, with their impossibly long necks and tails, became the undisputed titans of the land. Diplodocus, Brachiosaurus, and Apatosaurus grazed on immense quantities of foliage, their sheer size a defense against the formidable predators evolving alongside them. Allosaurus, with its powerful jaws and serrated teeth, stalked these vast woodlands. The air was warm, the seasons mild, providing an ideal environment for unchecked growth and diversification. Life had found a way to not just exist, but to flourish on an unimaginable scale. Each tooth and claw part of a sprawling, intricate web of existence that seemed both robust and perpetually hungry. The Cretaceous period brought further radical changes. The continents continued their drift, shaping the oceans and land masses into forms more recognizable to modern eyes. Crucially, flowering plants, angiosperms, began to spread across the globe. This evolutionary leap offered new food sources, in turn driving further specialization among herbivorous dinosaurs. Triceratops, with its iconic frill and horns, and the armored Ankylosaurus became prominent. Tyrannosaurus rex emerged as the apex predator of North America, a creature of immense power and presence. The world was a mosaic of diverse ecosystems, each teeming with specialized dinosaur forms, showcasing the incredible plasticity of life to fill every conceivable niche. Beyond the terrestrial giants, the Mesozoic skies and oceans also hosted their own dynasties of colossal reptiles. Pterosaurs, not dinosaurs, but close relatives, ruled the air. From the small, agile pterodactylus to the truly immense Quetzalcoatlus, with its wingspan of a small aircraft, these creatures mastered flight in various forms. In the oceans, marine reptiles like the serpentine plesiosaurs and swift ichthyosaurs commanded the waves, pursuing fish and other sea life with unparalleled efficiency. The parallel evolution of these aerial and aquatic behemoths illustrated a planetary ecosystem where large reptiles dominated every possible domain, a testament to a grand ecological unfolding. The sustained reign of dinosaurs, spanning over 160 million years, remains an enduring mystery and a profound testament to evolutionary success. What combination of factors allowed them to thrive for so long? Was it their incredible adaptability, their rapid evolutionary rates, or the very structure of the continents and climate of the Mesozoic? Their success seems to whisper of a deep attunement to their world, a synergy that allowed them to navigate changing landscapes and new ecological challenges with remarkable resilience. This unprecedented dominion forces us to consider the very nature of biological longevity and how such an age could suddenly and violently end, as we will explore with the impact event. The end was not a slow fade, a gradual decline of the Titans. It was an instant, cataclysmic strike from beyond our world, an event etched into the planet's very crust. We speak of the KPG impact, the moment an extraterrestrial body collided with Earth, wiping clean much of the life that had defined an era. This impact signature, a thin layer of iridium-rich clay, marks a boundary in the geological record, a visible scar of extreme violence. This scar on our planet, known as the Chicxulub crater, lies beneath the Yucatan Peninsula. Its very existence was once debated, hidden beneath layers of sediment, but its circular gravity anomaly and the telltale shock minerals confirmed its identity. The asteroid, estimated to be at least 10 kilometers across, struck with an energy release equivalent to billions of times the atomic bombs dropped on Hiroshima. This was not merely a significant event. It was an unimaginable explosion, the likes of which humanity has never directly witnessed. The force was so immense, it briefly turned the rock beneath it into a superheated plasma, vaporizing tons of material instantly, creating a crater over 180 kilometers wide. The immediate aftermath was a global firestorm as the asteroid plunged into the shallow seas of the Yucatan. It launched an unimaginable plume of superheated rock and dust high into the atmosphere. This ejecta, accelerated to hypersonic speeds, re-entered the atmosphere across the globe, incinerating everything in its path. Imagine a sky suddenly filled with incandescent meteorites, raining down fire and heat, igniting forests and grasslands across continents. Simultaneously, a monstrous shockwave rippled outwards from the impact site, tearing through the atmosphere and crust. Earthquakes of unprecedented magnitude shook the planet, triggering massive landslides and volcanic eruptions. The impact in the ocean also generated colossal tsunamis that scoured coastlines thousands of kilometers away, leaving behind chaotic deposits of marine and terrestrial debris far inland. These events were not isolated. They were interwoven into a tapestry of instantaneous and widespread destruction, a planetary convulsion. Yet the raw power of the initial strike was merely the beginning of the long nightmare. The colossal amount of dust, soot from global wildfires, and sulfur aerosols injected into the stratosphere formed a thick, impenetrable veil. This cloud choked the skies, blocking out the sun's light for months, perhaps even years. Without sunlight, temperatures plummeted across the globe, plunging Earth into a prolonged impact winter. Photosynthesis, the foundation of most ecosystems, ground to a halt, causing plants to die en masse. The herbivores starved, and in turn, the carnivores followed. This was a slow, agonizing suffocation after the initial inferno. Beyond the darkness and cold, there was another insidious killer at work: acid rain. The Yucatan bedrock, rich in sulfates, was vaporized by the impact, releasing vast quantities of sulfur dioxide into the atmosphere. This gas combined with water vapor to form sulfuric acid, which then rained down across the planet. This acid rain poisoned freshwater sources and stripped nutrients from soils, further devastating land plants. The oceans, too, suffered severe acidification, dissolving the shells of marine organisms at the base of the food chain, causing a mass extinction in the water as profound as on land. This cascade of environmental collapse created a world almost unrecognizable to the one that existed moments before. But from this crucible of destruction, a new world began to emerge. The ecological niches, once dominated by the dinosaurs, were now vacant, open for new forms of life to exploit. Small, adaptable creatures, often burrowing nocturnal and capable of enduring scarcity, survived the prolonged environmental winter. Among these were the early mammals. With the giants gone, they began an astonishing period of diversification, radiating into countless forms and sizes, seizing the opportunities left behind. This global catastrophe, though devastating, was the violent midwife to a new era, directly paving the way for the Cenozoic era and the rise of mammals. The Earth breathes, not in seconds or minutes, but in cycles of immense glacial advance and retreat. These rhythmic pulses of ice have sculpted landscapes and shaped life itself, offering a profound counterpoint to the catastrophic impacts of earlier epochs. We now move into a more recent chapter, where the canvas of our planet was repeatedly painted with vast, moving sheets of ice. This grand orchestration of climate change, these alternating eras of frigid grip and temperate release, finds its origin in the subtle, yet powerful influence of celestial mechanics. We speak of the Milankovitch cycles. These are not sudden, violent impacts, but rather gradual, predictable shifts in Earth's orbital parameters. Imagine the slow, almost imperceptible wobble of a spinning top, or the slight widening and narrowing of its circular path around a central point. Earth's tilt, the eccentricity of its orbit, and the precession of its equinoxes all shift over tens and hundreds of thousands of years. These astronomical factors subtly alter how much solar radiation reaches different parts of the planet, particularly at high latitudes, nudging the global thermostat just enough to initiate either a deepening chill or a slow thaw. It is a cosmic dance, unseen by the casual observer, yet its effects cascade across the entire globe, determining whether snows remain to become ice or melt away to fuel rivers. But the scale of the ice sheets generated by these subtle shifts is almost beyond comprehension, setting the stage for continental transformations. With the persistent chilling effect of altered solar insolation, the snows began to fall, and crucially, to stay. Over millennia, layers piled upon layers, compacting under their own immense weight into vast, sprawling continental ice sheets. These were not mere caps on mountain peaks. They were titanic masses, miles thick, stretching across continents like an unstoppable geologic force. In North America, the Laurentide ice sheet grew to cover much of Canada and extended deep into what is now the northern United States, while in Europe, the Scandinavian ice sheet spread its frosty embrace. As these ice sheets grew, they did not sit still, fueled by gravity and the plasticity of ice under tremendous pressure. They flowed outward, grinding slowly but incessantly across the land. This movement was a colossal erosional engine, tearing away bedrock, scouring out ancient river valleys, and carving out the characteristic U-shaped valleys we see in glaciated regions today. The Great Lakes themselves are a testament to this immense sculpting power. Colossal depressions gouged out by these moving behemoths. Every mile of advance meant a reshaping of the land beneath, a new topography born from the patient, grinding work of ice. As these frozen rivers crept across the land, an even more dramatic transformation was unfolding at the very edges of the continents. The sheer volume of water locked away in these colossal ice sheets had a profound and visible consequence for the global oceans. Imagine oceans shrinking, not by a gentle ebb, but by a continuous, massive withdrawal. As ice sheets grew, they siphoned water directly from the world's oceans, converting liquid into solid, year after year, millennium after millennium. This titanic transfer of water resulted in a dramatic lowering of global sea levels, sometimes by as much as 120 meters, or nearly 400 feet. During the peak of glacial periods, coastlines retreated, exposing vast expanses of continental shelf that had been submerged for millennia. Land bridges emerged, connecting continents that are now separated by wide stretches of water. The Bering Strait, for instance, became the Bering Land Bridge, allowing the passage of animals and eventually humans between Asia and North America. Australia, Tasmania, and New Guinea were joined into a single landmass called Sahel. The outlines of the world map shifted profoundly, creating new migration routes and isolating populations as the water returned. This rhythmic fall and rise of the sea surface was a fundamental pulse, dictating the movements and distribution of terrestrial life and forcing life to adapt to ever-changing coastal geographies. Life, caught in the grip of these glacial oscillations, responded with remarkable adaptations. The colder, harsher climates of the ice ages favored species able to withstand extreme temperatures and exploit scarce resources. This era saw the emergence and dominance of iconic megafauna, creatures of immense size and specialized features. Woolly mammoths, with their thick coats and insulating layers of fat, roamed the vast, cold steppes, grazing on tough grasses and sedges. Saber-toothed cats, powerful predators, hunted these giants, giant ground sloths, woolly rhinoceroses, and Irish elk, with antlers spanning impressive widths, all populated these icy landscapes. Their large size provided a more favorable surface area to volume ratio, helping them retain body heat in the biting cold. They developed specialized diets, thick fur, and adapted behaviors to survive in a world fundamentally different from the temperate forests that preceded and followed these glacial periods. However, as the planet began to warm and the ice sheets retreated, many of these magnificent creatures faced new challenges. The shifting climate, changes in vegetation, and perhaps human predation all contributed to a wave of extinctions that swept through the megafauna at the end of the last glacial period. This era of colossal ice and colossal beasts offers a glimpse into life's struggle for survival and its capacity for adaptation. But even this dance of ice and life was merely a preamble to the epic that would see one species rise to dominate the planetary stage, deeply intertwining its fate with Earth's history, the Holocene, and the ascent of humanity. The Earth's crust holds whispers, not just of continental shifts and ancient oceans, but of footsteps, not the heavy tread of dinosaurs, nor the scraping of glaciers, but the delicate impressions left by creatures taking their first upright steps. These are the Australopithecine footprints at Litali, a fossilized moment etched into volcanic ash, uncovered in what is now Tanzania. Here, some 3.6 million years ago, a small group of hominids, likely Australopithecus afarensis, walked across a fresh layer of ash, dampened by rain, then quickly covered by another eruption. These footprints are not just fossilized mud. They are a direct communication across vast spans of time, a visual confirmation of bipedalism at a remarkably early stage of our lineage. We see a distinct heel strike, an arch, and a toe-off, patterns uncannily similar to modern human gait. 2 or 3 individuals walked side by side, their tracks perfectly preserved, speaking of social units, perhaps even a family. This brief, silent procession offers a profound connection to our very distant ancestors, hinting at sophisticated locomotion long before complex brains or elaborate cultures. It is a portal into a time when the world was wild and untamed, yet already resonating with the first stirrings of what would one day become us. This initial mastery of upright walking, freeing the hands, laid the foundational stone for tool-making, an innovation that would forever alter the course of life on Earth. The question then becomes, what did these newly freed hands begin to create? And what did those creations tell us about their minds? This leads us to the Alduin Industrial Complex. The Alduin Industrial Complex represents the very first unquestionable evidence of stone tool manufacture, dating back as far as 2.6 million years ago, enduring for nearly 1 million years. These tools are deceptively simple, river cobbles, often quartz or basalt, struck with another stone to produce sharp flakes, and a core with an acute edge. Yet their simplicity belies their revolutionary nature. This was not random breakage. This was deliberate modification of the natural world, a direct intervention to shape environment for advantage. The flakes, razor sharp, could cut meat from bone, scrape hides, and process plant material. The cores themselves could be used for chopping or pounding. This technological leap signified a profound shift in cognitive ability. It required foresight, planning, and a precise understanding of fracture mechanics, a crude form of physics. It meant hominids were no longer solely reliant on what nature provided, but could actively create what they needed. The widespread distribution of Alduin tools across Africa, from Ethiopia to South Africa, marks the beginning of a technological lineage that stretches unbroken to the present day. This sustained development and transmission of knowledge suggests increasingly complex social structures and learning. But as these tools spread, so too did their makers, venturing out beyond their African cradle. It is this journey, these vast movements across continents, that we call the out of Africa migrations. The story of human expansion is a narrative of relentless movement, driven by an inherent curiosity and the exigencies of survival. The first major wave, sometimes called Homo erectus's exodus, began around 1.8 million years ago, spreading across Asia to places like Dmanisi in Georgia, and then East Asia. These early pioneers were not just driven by a wanderlust, but by the ebb and flow of climate, the availability of resources, and perhaps even demographic pressures. Later, modern Homo sapiens, emerging from Africa around 0 to 70 years ago, embarked on an even more ambitious set of journeys, navigating vast landscapes, overcoming formidable geographical barriers, and adapting to radically different environments. These migrations were not single, continuous events, but a series of waves, often diverging, sometimes merging, shaped by glacial cycles that exposed land bridges and lowered sea levels. Each step was a gamble, a test of ingenuity and endurance, leading to the peopling of every habitable continent. The genetic traces left behind in modern populations tell a story of these ancient odysseys, mapping routes across deserts, through forests, and along coastlines. This relentless expansion brought our ancestors into contact with other hominin species that had already established themselves in various parts of the world. One such encounter, particularly poignant, involves the sophisticated inhabitants of Ice Age Europe, the Neanderthal endings and encounters. For hundreds of thousands of years, Neanderthals thrived across Europe and parts of Asia, adapting brilliantly to the harsh, fluctuating climates of the Ice Age. Their culture, once dismissed as brutish, is now revealed as complex and nuanced. They buried their dead, sometimes with grave goods, suggesting a belief system, or at least a deep respect for the deceased. They crafted sophisticated tools of the Mousterian tradition, engaged in hunting large game, and even wore personal adornments like shell beads and eagle talons. Their anatomy, robust and powerful, was perfectly suited to their environment, and their brains were, on average, slightly larger than those of modern humans. Then, around 40,000 years ago, modern humans arrived in Europe, encountering these established populations. What followed was not a simple replacement, but a complex interplay of interaction, competition, and interbreeding. Genetic evidence clearly shows that Neanderthals contributed DNA to non-African modern human genomes, meaning our ancestors had intimate encounters. Yet, within a few thousand years of modern human arrival, the Neanderthals vanished from the fossil record. Their disappearance remains one of the great mysteries of human evolution. Was it climate change, competition for resources, violence, or perhaps absorption into the larger, more adaptable Homo sapiens population? The echoes of their presence still resonate in our genes, a silent testament to a shared past. Yet, even as we sift through the known layers of our heritage, there are tantalizing glimmers of an even deeper, more elusive past, challenging our understanding of human presence, hinting at the ghost of pre-ice age inhabitation. The conventional narrative places widespread modern human expansion within the last 100 years, largely after the peak of the last glacial period. However, geological records and controversial archaeological findings hint at a more complex, perhaps earlier, human presence in regions now submerged or obscured. As sea levels rose dramatically at the end of the last glacial maximum, vast coastal plains, once fertile hunting grounds and vital migration corridors, were swallowed by the oceans. Any evidence of human activity in these drowned landscapes now lies beneath miles of water, effectively erased from easy discovery. Consider the Beringia land bridge, which connected Asia and North America. While its role in the peopling of the Americas is well established, what if earlier hominins, perhaps even earlier waves of Homo sapiens, crossed it during previous low sea level stands, only to have their traces covered by subsequent glacial advances or oceanic transgression? Evidence of early habitation in unexpected places, such as disputed claims of hominin activity in North America dating back over 100 years, challenges established timelines. These faint, often ambiguous signals suggest the possibility of earlier forays, perhaps ephemeral presences, lost to the relentless grinding of geological time and the shifting face of the earth. These ghosts of pre-ice age habitation force us to consider what profound truths remain hidden, waiting to be revealed by the relentless erosion of time or the probing tools of future discovery. And as we ponder these lost worlds and forgotten timelines, we must also consider the profound and accelerating impact of our own species on the planet. As we delve into the story of the Anthropocene and the age of human dominion, the Earth's rhythm is not always a slow, steady drumbeat. Sometimes it is a sudden, jarring chord, a rapid plunge into an unexpected state. One such moment, relatively recent in the grand sweep of deep time, was the Younger Dryas event. This was not a gradual cooling, but a violent lurch backward, a dramatic re-embrace of glacial conditions that lasted for over 1,000 years. It arrived with an almost unthinkable speed, plunging large parts of the northern hemisphere back into an ice age, just as the world seemed to be warming into a gentle interglacial. The causes of this sudden chill and its profound impact on early human populations are still whispers in the stone, demanding our quiet attention. At the heart of the northern hemisphere's climate stability lies a vast, invisible engine, the North Atlantic's thermohaline circulation. This deep ocean current, often referred to as the Atlantic Meridional Overturning Circulation, or AMOC, acts like a planetary conveyor belt. It pulls warm, salty surface waters northward from the tropics, releasing heat into the atmosphere, which then warms Europe and parts of North America. As these waters cool and become denser, they sink, returning south as deep currents. This continuous loop is a vital modulator of climate, a silent, powerful guardian of regional warmth. But this guardian is deeply sensitive, particularly to the influx of fresh water. Its delicate balance can be tipped with surprising ease. The Younger Dryas was triggered by just such a tipping point. Massive meltwater pulses as the last great ice sheets began their retreat. Vast quantities of fresh water, trapped for millennia, were suddenly unleashed into the North Atlantic. Imagine enormous glacial lakes, dammed by ice, suddenly bursting their boundaries. This deluge of cold, fresh water, less dense than the salty ocean, effectively created a cap on the surface. It disrupted the sinking mechanism of the AMOC, weakening or even temporarily shutting down this crucial oceanic circulation. Without its warm embrace, the northern hemisphere quickly plunged into a deep freeze, a stark reminder of the planet's intricate, interconnected systems and their capacity for sudden, dramatic shifts. The human world, then on the cusp of significant cultural development, found itself abruptly thrown into disarray. In North America, the Clovis culture, characterized by its distinctive fluted projectile points and a lifestyle adapted to hunting megafauna, mysteriously vanishes from the archaeological record almost precisely at the onset of the Younger Dryas. Their sudden disappearance or transformation coincides too neatly with the environmental pressures of this swift, return to Ice Age conditions to be mere coincidence. The vanishing of their prey altered migration routes, and the sheer brutality of the cold would have tested any society to its breaking point. What became of these skilled hunters, and how did they adapt to such a rapid and profound environmental upheaval? The stone tools fall silent, but the questions linger. Perhaps paradoxically, this sudden climate instability became a radical catalyst for human innovation. Forced to adapt or perish, some theories suggest the younger Dryas played a crucial role in accelerating the transition from nomadic foraging to settled agriculture. As traditional food sources became scarce or unpredictable, the need to control plant cultivation and animal domestication would have become paramount. The harsh lessons of survival during this epoch of sudden chill may have planted the seeds for civilization itself, forging a new, more intimate, and ultimately transformative relationship between humanity and the land. To understand the depth of this transformation, we must next delve into the profound and accelerating impact of our own species on the planet. As we explore the story of the Anthropocene and the age of human dominion, the Earth's surface, as we know it, is merely a fleeting snapshot in deep time. Beneath the ceaseless rhythm of the ocean waves lie vast plains and ancient river valleys, submerged continents, now silent witnesses to a past profoundly different from our present. These hidden landscapes speak of a time when the seas were not where they are today, and land bridges connected places now separated by impassable waters. One such ghost in the ocean's depths is Doggerland. Imagine a fertile, rolling plain stretching from what is now the east coast of Britain across to continental Europe. This was not a narrow strait, but a vast expanse of land teeming with life, threaded with rivers, and likely home to early human hunter-gatherers. During the last glacial maximum, when massive ice sheets locked away enormous volumes of water, global sea levels plummeted, revealing this entire subcontinent. Its rivers flowed into a central basin, forming a freshwater lake before eventually draining into the ancient North Sea. Evidence from trawler nets, pulling up tools, bones of mammoths, and even human artifacts, offers tantalizing glimpses of a verdant world now lost beneath the waves. The gradual melting of the ice sheets, a slow and relentless process, eventually reclaimed Doggerland, swallowing its rivers, its forests, and any settlements it may have harbored. This wasn't a sudden cataclysm, but a creeping inundation, forcing its inhabitants to retreat or be consumed by the advancing sea. Similarly, in Southeast Asia and Australia, extended landmasses known as Sunda and Sahel emerged during periods of lower sea levels. Sunda connected mainland Asia to the islands of Sumatra, Java, and Borneo, creating a vast, continuous plain. Sahel, on the other hand, joined Australia with New Guinea and Tasmania. These colossal land bridges were vital highways for early human migration, allowing our ancestors to traverse immense distances that are now impossible without sea travel. The geographical continuity offered by Sunda and Sahel provided pathways for the spread of flora and fauna, shaping the unique biodiversity of these regions even after the waters rose again. The precise routes and timings of these migrations are written in genetic markers and archaeological finds, but much remains hidden, waiting to be discovered in the now submerged coastal zones. Further east, the Black Sea holds a different, perhaps more dramatic, narrative of inundation. The theory suggests that what is now a vast saltwater sea was once a much smaller freshwater lake. As global sea levels rose following the last ice age, the Mediterranean Sea, brimming with its own increasing volume, eventually breached the natural land barrier at the Bosphorus Strait. This was not a gradual seepage, but potentially a catastrophic torrent, a massive freshwater flood that transformed the ecosystem and geography of the region in a relatively short period. Imagine the roar of the incoming salt water, the rapid drowning of coastal communities, and the irreversible alteration of a freshwater world into a saline one. This event, if it occurred as theorized, would have erased entire landscapes and shifted human populations, perhaps even seeding ancient flood myths. Beyond these relatively recent deluges, deep time reveals far more profound erasure through tectonic subduction. Entire continental fragments, vast island chains, and ancient ocean floor have been relentlessly consumed by the Earth's mantle. As one tectonic plate slides beneath another, immense forces drag crustal material down, melting and recycling it. This process is a silent, continuous obliteration of geological history. Imagine ancient continents, once thriving with unknown life forms, and perhaps even early hominids, now completely dissolved within the planet's interior. Every trace, every fossil, every geological record is simply gone, leaving no direct evidence on the surface. These are the truly lost worlds, the ultimate submerged continents that leave no trace for us to find. Only a theoretical understanding of their immense scale. Looking forward, the specter of future sea level rise looms large as our climate continues to warm and glaciers melt. A new chapter of submersion is already unfolding. Coastal cities, low-lying islands, and vast swathes of fertile land are facing inevitable inundation. The maps of our very near future will be redrawn, not by ancient ice ages, but by our own actions. What currently stands as firm ground will become the next Doggerland or Sunda, silently accepting the encroaching waters, erasing familiar coastlines and displacing millions. This ongoing transformation forces us to consider not just the hidden past, but the imminent future of our land and oceans, leading us to contemplate the profound geological transformations that shaped the very bedrock of our world. As we turn our attention to the ancient story of continental drift and the dance of the continents. Beneath our feet, the Earth breathes in geologic time, a slow, continuous expansion and contraction that reshapes continents and oceans. This breathing is the grand rhythm of supercontinent cycles, a process so vast it dictates the very essence of life and climate over hundreds of millions of years. The surface of our planet is not a static canvas, but a dynamic tapestry of colossal plates, constantly in motion. These enormous lithospheric slabs ride atop the semi-fluid mantle, driven by the planet's internal heat. This engine, known as plate tectonics, is the silent architect of our world, responsible for the deep trenches where oceanic crust dives back into the earth, and the soaring mountain ranges where continents collide. It is a slow, relentless ballet where landmasses drift apart, oceans widen, and then, in time, reverse course, drawing together once more. This seemingly imperceptible movement, measurable in mere centimeters per year, accumulates over eons to produce transformations of unimaginable scale, culminating in the assembly of a single colossal landmass. This is the dance of the plates, a cosmic waltz that has been replaying for billions of years, each cycle leaving its indelible mark on the planet's story. It is a story of creation and destruction, of mountain building and ocean opening, a constant reshaping that underpins all life. Long before Pangaea, there was Rodinia, an ancient supercontinent whose formation and breakup left an enduring legacy on early Earth systems. Assembled between 1.3 billion and 900 million years ago, Rodinia was a stark, barren world, its vast landmass stretching across the planet. Its assembly initiated a profound cooling event, a global glaciation known as Snowball Earth. The immense continental mass reflected more sunlight, and the weathering of its exposed rock drew down vast amounts of carbon dioxide from the atmosphere. This supercontinent's existence reshaped ocean currents, creating conditions ripe for the diversification of early life forms, even as it ushered in an era of extreme cold. The rifting apart of Rodinia, starting around 750 million years ago, unleashed a new wave of tectonic and climatic changes, flooding coastal shelves and releasing trapped nutrients into the oceans, setting the stage for the burst of life that would follow. Its distant echoes still resonate in the cratons that form the heart of modern continents, silent witnesses to a planetary past. But Rodinia was not the last of these colossal unions. The more familiar Pangaea, meaning all lands, was the last great supercontinent, formed approximately 335 million years ago. Its assembly brought together nearly all of Earth's landmasses into a single, immense entity. Imagine a world where you could walk from the South Pole to the North Pole without crossing a major ocean. Pangaea's vast interior experienced extreme continental climates, scorching deserts in summer, brutal winters in others, far from the moderating influence of the sea. This global warmth, driven by the supercontinent's configuration, shaped the evolution of reptilian life, allowing them to thrive in arid conditions. The extensive coastlines, while limited in number, fostered unique marine ecosystems. The formation of Pangaea also led to a significant drop in global sea levels, as there were fewer mid-ocean ridges to displace water. This supercontinent, a singular landmass dominating the globe, profoundly influenced ocean currents, atmospheric circulation, and the distribution of species, leaving a distinct fossil record that binds disparate modern continents together. The evidence of its existence is etched into the very rocks of our planet, a testament to a time when all land was one. The presence or absence of these supercontinents profoundly influences the Earth's climate and biological evolution. When continents are scattered, their coastlines increase, leading to more moderate global temperatures, as ocean currents can distribute heat more effectively. Conversely, a single supercontinent creates more extreme climates, with vast interior deserts and a less efficient global heat distribution system. Supercontinent cycles dictate sea levels, atmospheric composition through the weathering of exposed rock, and even the frequency of volcanic eruptions. They are the slow, deep breath of the planet, regulating the conditions for life itself. The Earth's geological heartbeat is measured in these colossal unions and separations, each one a canvas for new life forms and new planetary states. From the frigid grip of snowball Earth, triggered by Rodinia, to the arid expanses of Pangaea, continentality's climate impact is undeniable, shaping the very air we breathe and the water that sustains us. And the dance continues. Geologists and geophysicists, looking far into the future, speak of Pangaea Proxima or Pangaea Ultima, the theorized next supercontinent. Our current continents, imperceptibly slow, are still drifting. Africa is slowly rotating towards Europe, closing the Mediterranean Sea. Australia is moving north towards Asia. The Atlantic Ocean is widening, while the Pacific is slowly shrinking. In approximately 250 million years, a new supercontinent is projected to form, bringing the disparate landmasses of today back into a grand embrace. Imagine a future Earth where maps are redrawn beyond recognition, where the familiar outlines of continents are swallowed into a single, colossal landmass. This distant whisper of Pangaea Proxima reminds us that our present world is but a fleeting moment in the Earth's eternal cycle of creation and destruction, a future that will be shaped by the inexorable drift of the continents. As we gaze forward into this deep future, we must also look deep into the past, into the processes that have woven the very fabric of our geological time. revealing how the Earth's core continues to drive these surface transformations. Make sure to subscribe for more videos and hit that notification bell so you never miss a new video. We'll see you in the next one.